Hi, my name is Thierry Tambe. I am a PhD student at Harvard University. I am pleased to be invited to give this talk at the second workshop on Agile Research Test Chip by ISCA. This talk is about closing the algorithm hardware design and verification loop with speed via high-level synthesis. So let's get started. So we know that Dennard scaling is flattening, and as a result of that, engineers are no longer able to achieve higher energy efficiencies by just scaling the transistor length. So this has spurred the rise of domain-specific accelerators with many hardware optimization done to extract better performance. For example, we see in this picture that the number of specialized IP blocks or accelerators have been increasing steadily over the years. And as you can imagine, this means that SoCs are getting more and more complex, with design efforts also increasing as a result of this. So there is definitely here a motivation for a more agile and faster way to design chips. And this is where high-level synthesis can be extremely helpful. So beyond sharing or reusing key system parts, designers can save a tremendous amount of time by raising the level of abstraction of their design to C++ or SystemC, and then use a high-level synthesis tool to convert the C++ design to RTL. So why use HLS? So besides designing in a more abstract way, HLS also enable rapid architectural exploration. It performs automatic scheduling, resource sharing, and pipelining. And I think one of the major benefits of HLS is that it allows you to use the C++ test bench to verify the HLS generated RTL. So there is no need to create a separate RTL test bench to verify the Verilog produced by the HLS tool. I think this is very important. HLS also allows for easy retargeting to different silicon technologies. And when it comes time to debug the hardware, most of the debugging happens at the abstract C++ level as opposed to debugging at the RTL level. So a great example of this front-end HLS design flow is the OOHLS flow, object-oriented HLS flow, summarized in this seminal paper at DAC 2018. In the next few slides, I will provide some backgrounds and more details on some of these components. So this is a non-exhaustive list of HLS tools out there. As you can see, many tools offer commercial licenses, and some offer academic open source free licenses. I should preface the rest of my talk by saying that many of the information that I'm about to share was done using Catapult, and therefore some information may not be compatible with other HLS tools. That said, the goal of this talk is not to compare HLS tools, and definitely the intent is not to advocate for the usage of Catapult. It's just that Catapult is the tool that I'm most familiar with. And also I would say that although the information I'm about to share was done with Catapult, I would say some of the tips and learnings can be applicable to other HLS tools as well. So in this talk, I will quickly go over some of the most important C++ component and features for HLS. Then I will shed light on constructing a software, hardware, co-design, and co-verification framework to aid in the design of a correct by construction hardware accelerator. Finally, I will share some tips and pitfalls to avoid for working in this HLS augmented algorithm hardware framework. So for complex design, it is highly advantageous to use SystemC, which is a library built on top of C++, to design system and also architecture simulation, and to perform architecture simulation. The inner working of SystemC is event-based, and therefore and it also allows for multi-thread programming, which means that multiple parallel processors can work simultaneously, and this can help maximize the throughput of your design. When using SystemC, the highest level block will be the SystemC module. This is analogous to Verilog module, if you are familiar with Verilog. So the SystemC module contains a list of processes which will be defined in the SC constructor. And the SC module is verified in a test bench, which contains the SC_main function. Inside the SystemC module, you may instantiate one or multiple C++ functions. These functions typically use arguments as input and return a value as output. And they can be verified in a separate test bench containing the CCS_main function. So there are already some open source synthesizable C++ component available out there. A popular and very useful one is MatchLib. These MatchLib components shown here in this picture already encapsulate verified functionality, and they have been already optimized for QOR. Therefore, in many cases, you don't need to reinvent the wheels. If you're looking for some common functionality, such as scratchpad, routers, and channels, you can just instantiate the appropriate MatchLib component. MatchLib also provide a variety of data types and bit slicing mechanism. They are also vector data types, which you can use to perform vector computation or to construct a BLAS-like function such as matrix multiplication. The full list, the most up-to-date list is available on this website, so definitely take a look here. Another very useful synthesizable library is called the HLS lib fomenter. And this library contains a variety of mathematical functions. I would say that many of the functions available in the non-synthesizable math.h library can be found in the synthesizable HLS lib library. So this can be very useful in addressing many accelerators design. And HLS lib also contains a variety of so-called algorithmic C data types, such as integer, fixed point, and floating point. In fact, I should point out that many of the MatchLib data types already make use of these AC data types. Now let's talk about channel, because this is a very important topic in C++ design for HLS. So why do we need channels? So recall that the processors inside a SystemC module can only access variable declared inside the module. So we need a channel to make these variable accessible by external SystemC modules. There are some native channels available out there, especially within the SystemC.h library. These channels are templated and can be declared as input, output, or as a signal channel, as shown in this picture. So the signal channel obviously will be used to connect between two input and output channel port. Now, wherever possible, it would be best to use latency insensitive channels from MatchLib. As shown here in this picture, these channels orchestrate a two-way handshaking mechanism between the producer and the consumer. There are two control signals in the latency sensitive channels, valid and ready. The message is sent from the input port to the output port only when the producer only when the producer message is valid and the consumer is ready to receive that message. There are blocking and non-blocking flavors for these latency sensitive channels. And so you would use push or pop, for a blocking mechanism, and push NB and pop NB for a non-blocking mechanism. Push is used obviously to send the message, and pop is used by the consumer to receive the message. Now let's quickly differentiate between the non-blocking and the blocking channel. By the way, both blocking and non-blocking channels for MatchLib implement this two-way handshaking mechanism. When using a blocking push and pop, the SC thread will stall until the message is sent or received. So you may wonder why we would ever want to stall a process. In fact, using a blocking push and pop can be useful in controlling the start of an event. So for example, starting a multiply and accumulate computation upon receiving the enable signal. So this is a very specific scenario where you would need to actually use a blocking channel. Obviously, there are many scenarios for which we don't want to create deadlocks. And in this case, we would use a non-blocking channel. So here, if the message can be sent or received, the non-blocking channel will return true. Otherwise, it will return false. Another type of latency insensitive channel is the buffered channel. Essentially, these channels are augmented with FIFOs. Notably, this can be very useful in avoiding deadlocks, especially when you have multiple senders or receivers. And to show an example, you may have a scenario where you have multiple senders, sending their message to a single receiver. So this can be solved by using an arbitrated crossbar. MatchLib provide such a class that you can simply instantiate in your design to arbitrate this traffic. As you see here, obviously the input to the crossbar must be buffered in order to avoid potential congestion. In the reverse scenario, in case a sender needs to broadcast the same message to multiple receivers, obviously the output port of the broadcasting channel needs to be buffered as well by using these buffered latency sensitive channels. So now that the background is covered, I would like to deep dive on constructing a software hardware co-design and co-verification flow using HLS. So say that you want to design an accelerator, a hardware accelerator for speech to text, and you want the accelerator to be functionally correct and faithful to the software model. So to start, you would provide a pre-trained model to a deep learning framework such as PyTorch, TensorFlow, or Keras. And we want the accelerator to be able to work with quantized operands. So in the deep learning framework, we would perform quantization. We may also perform weight clustering, and also even perform pruning, and to essentially have sparsity on the weights of the neural network. So doing this, as you know, can help us produce higher energy efficiencies and higher compute density. Then we will ship the data, the weights of the neural network, to our HLS design and verification workbench shown here. Now, how do we, send the weights to the HLS workbench? I think these ML frameworks, all of them should have a Python API. So we can use the NumPy Python package to export weights of the neural network in the .mpy format. And then in the C++ test bench, we can instantiate the libmpy C++ library to be able to read NPY files. In the C++ design, you can save a tremendous amount of time by using already available synthesizable components such as MatchLib and HLS-lib, which I discussed earlier. And definitely, I would say it is important to spend some time investing in a very detailed, parameterizable, and high coverage test bench with checkers. I would say that the investment in this step will be very rewarding down the line. So then we close the loop between the software and the hardware by comparing the activation between the software model and the activation produced, computed by the hardware accelerator. So in case the value of the software and the hardware activations are equal, we can proceed to high-level synthesis. Otherwise, we need to fix the bug in the C++ design. Obviously here, the software model is assumed to be golden, so the bug fixes need to go only to the C++ design. And after high-level synthesis, we should also look back to the C++ design in case the RTL verification is incorrect, or in case the power, performance, and area metrics are not satisfactory. In fact, it is critical, I believe, to perform this entire loop within the HLS environment as much as possible for the fastest turnaround. Many HLS tools out there, especially the commercial ones, already provide built-in capabilities to extract the post-HLS PPA from the design, and this definitely helps facilitate this feedback loop. Okay, now I want to share our experience and provide some useful tips, especially on the HLS front for an effective and reliable accelerator or system design. Let's first start with some pitfalls to avoid. If you are just getting started with high-level synthesis, you will most likely notice that it can be tricky to write a C++ source code that is functional, synthesizable, and RTL verifiable all at the same time. For example, in some cases, you may write a code that passes compilation and C++ verification, but actually fails during the final RTL verification. This is actually illustrated here in this code, which implement FSM transition states. So you see here that in case we accidentally omit the next state transition in the default case here, we saw that this actually will pass the C++ simulation, but it would fail eventually during the RTL verification. So as you can imagine, this can be somewhat frustrating because you may only catch these kinds of bugs much later during the final RTL verification. So I get the sense that there is a lack of standardized coding guidelines to guarantee end-to-end functional correctness, all the way from C++ to final RTL verification. So therefore, I think designers should be wary of this and really spend time to sanitize the C++ code prior to HLS. We've also seen that poor C++ coding could lead to poor PPA after HLS. Oftentimes, this is due to long data dependencies. In example here, the code on the left actually produces a higher area than the code on the right. And that is because we were accumulating the input directly onto the output without first storing the accumulation onto its temporary variable. Also, depending on how your source code is designed, pipeline scheduling can be challenging. Often you will not be able to achieve the desired initiation interval of 1 because of inherent logical dependencies in the design. So being able to detect and break these logical dependencies can enhance the overall performance of the design. This is a very important point. MatchLib provides a C++ construct called pacer that goes directly onto the C++ test bench, specifically onto the connection interfaces. And this can be useful in emulating and discovering at the C++ stage the various timing hazards that we may only see post HLS. Essentially, the pacer component injects random stores during the C++ simulation, and it may uncover bugs much earlier at the C++ stage instead of much later post HLS or even post place and route. So I highly encourage simulating your source code with pacer components. Also, do make heavy use of C++ function templates. These are extremely useful for parameterizable. They help maintain logic standards throughout the design. And definitely, they also make the design easier to read and easier to decipher. We found the synthesizable libraries such as MatchLib and HLS libs to be a huge productivity boost. We can definitely attest to the fact that these libraries played a huge role in helping us design and verify very complex accelerators in a matter of 2-3 months. So I definitely encourage leveraging synthesizable libraries such as MatchLib as much as possible. So as a case study, we designed an accelerator for natural language processing. And this table shows some of the components that were instantiated in the design from MatchLib and the components that were instantiated from the HLS lib. Not surprisingly, you see here that the connection channels, which I discussed earlier, along with the vector helpers, were by far the most instantiated component in this design. So to recap, number one, make heavy use of synthesizable library components. This can save you a tremendous amount of time in both the design and the verification. Number two, make heavy use of C++ function templates that make the design, really elegant and parameterizable. It's critically important to review and sanitize code for, for construct that may eventually lead to a non-optimal PPA. Also invest in a detailed and parameterizable test bench. I would repeat again that the time spent in this step will be very rewarding down the line when we need to do further optimization on the design. Augment the test bench with checkers, with really detailed, careful checkers to efficiently close the loop between the software modeling and the hardware. And finally, it's important to simulate the test bench with random stalls. This could be helpful in catching bugs much earlier at a C++ stage, as opposed to catching these bugs much later post HLS. So that's all I wanted to discuss today. I hope you found some of the information in this talk helpful. Thank you so much for watching this talk.